Hello and welcome to this edition of 30 Mechanical Minutes, virtual content for real-time professionals. I'm Doug Picklick, editor of HPAC magazine, and with me today is Ian McTeer, a regular HPAC writer on all topics related to HVAC, and Ryan Carr, business development and technical lead in Ontario at Air Solutions. Our subject matter today is all about heat and energy recovery ventilators, HRVs and ERVs. Sometimes it seems the V in HVAC often gets overlooked as people tend to focus on either heating or cooling. So today we're going to zero in on the air quality inside buildings. First, I'd like to acknowledge our sponsor for today's episode, and that is TSI Incorporated, a global leader in performance measurement solutions offering tools and instruments for the HVAC industry to measure and control ventilation systems and indoor air quality. Thank you very much for your support. And now just a couple of words about our speakers. Ian, as I said, has been a longtime writer for HPAC, and he's also an HVAC consultant and a retired field service representative with over 35 years of experience in the industry. And Ryan brings over a decade of experience, excuse me, and knowledge from his role as an HVAC channel professional. A certified trainer, Ryan's especially proficient in the areas of indoor air quality and the technical aspects of mechanical ventilation. Welcome to you both. Thank you.
Thanks for having us, Doug.
Thank you.
And for all of our watchers, today between our two guests, we have many years of on-site experience with ventilation systems. So if you have any questions, please type them into the Q&A section on your on-screen panel, and we'll try to get to all of your questions before we sign off in about 30 minutes from now. So let's begin. And Ryan, I'm going to start with you. So from a technology standpoint, maybe we can kind of start at the beginning, and if you could probably briefly describe the function of HRV and ERV systems and some of the technical differences inside these units.
Sure, yeah, be happy to. So, HRVs, ERVs, we often like to refer to them as kind of the lungs of the house, right? We all grew up going to grandma's house, paying her a visit, and, that house was drafty, right? You'd feel that air coming in. And, in that quest for energy efficiency over the years, as code has chased an ever more efficient house, we've had to tighten up that envelope, right? And we no longer have that natural air exchange. So we need to give the house lungs. So these devices, an HRV, a heat recovery ventilator, your core is either typically going to be plastic or aluminum. So those are what we often call inert materials, in that you can't push moisture through them, right? So the visual I like to create for a lot of people is think about a boiling kettle on a stove. You hold a thin sheet of plastic or aluminum over that spout, you'll certainly feel the heat. You might even burn your hand, but that moisture, that vapor in that water in that air is going to hit that surface and condense. It just simply cannot push through that material. So as houses have become tighter and more efficient, what we discovered was that the latent loads have become an ever-growing concern, right? The moisture. It's less about the heat loss, heat gain anymore, and more the moisture. So ERVs have become much more prominent, and that's an energy recovery ventilator. So it takes it a step further. So like the visual we see on screen here, not only the sensible heat is addressed, the physical temperature heat that you and I both feel, but also the latent heat or the moisture. So the core is a polymer reinforced paper. I like to think about it almost like a home wrap type material, and it's vapor permeable. And either an HRV or an ERV, we just rely on physics, right? Heat wants to go from hot to cold, moisture from wet to dry. And seasonally, as we see in this visual, an ERV allows both sensible and latent heat to transfer. So in the heating season, we've paid to condition that air, heat it, humidify it. Outside, it's cold and dry. So the last thing we want to do is, throw that air that we've paid to condition outside and replace it with that cold, bone dry air entirely. So that core not only allows for heat to transfer back to that incoming airstream, but also humidity. right? And that has been a shortcoming of HRVs. As houses have become tighter, we often hear complaints from occupants saying it feels dry, itchy eyes, scratchy noses, trim pulling away, and vice versa. In the cooling season, we're basically butting heads with our air conditioner. We're adding load. So the ERV helps us to reject that latent load back outside, and often allow us to actually bring down the sizing on our air conditioner.
Okay, good. Ian, anything to add on your experience with these units, maybe even in commercial environments if things are?
Well, it's been a long time, as I've said before. I think it was back in the late 80s or early 90s that I took a commercial ventilation course, and I honestly haven't kept up, but it was ASHRAE standard 62 at the time, which is now 62.1 for commercial buildings and 62.2 for residential applications. But of course, in Canada, we use the CSA F3280, I think, or 320, I think it is, for residential buildings. But when I first started doing elementary designs for commercial buildings, small rise commercial buildings, I mean, they hadn't even banned smoking yet. So once that was done, of course, the ventilation load could be cut much, I'm sure building owners love that idea because, of course, it reduced the load on their equipment. But as far as commercial buildings are concerned, there's so many things going on in them. There's so many different applications. There's, gymnasiums, there's restaurants, there's swimming pools, there's all kinds of applications, and it's definitely a delicate balance. Now, the engineers have been working on 62.1. Robert Bean, of course, would certainly know an awful lot more about that. But I discovered that in my own experience that commercial buildings, you often hear the term sick building syndrome. And a lot of it has to do with the fact that commercial buildings are very poorly ventilated, or actually sometimes they're overly ventilated to the point where the relative humidity drops to under 10% in some cases. And this causes people a lot of grief. And I just read an article yesterday or the day before about how people who are now being forced to work at home because of COVID are just so delighted because they actually have a half decent environment now, and their allergies and stuffy noses and dry skin and everything, all those issues have been solved, and they just literally do not want to go back to an office building. So obviously there's a lot of work to be done in commercial buildings when it comes to ventilation and a healthy environment.
Right. Well, so what about when it comes to the installation of these systems and the idea of right sizing a unit? I guess, and I mean, we do talk mostly, I think, about residential situations in homes. So Ryan, maybe you can just talk to us a little bit about how do you typically size a unit?
Sure. Yeah, happy to. I think as an industry, we have historically grossly oversized, right? It's always just sort of been a rule of thumb, right? Guy stands outside the house. That looks about 150 CFM, and by the time we plug that unit in, and then of course we look at the spot ventilation, so our 110 CFM main bath fan, or a couple other 50s and 80s for those other bathrooms, a 400 CFM range hood because everybody thinks they're Gordon Ramsay nowadays. We end up ventilating the living daylights out of these homes, right, and over drying them. Ian mentioned, the code reference there, CSA F320 for residential sizing, and actually what it looks at in a simplified installation, and we can take a look at the different installation methods, but the majority of new construction, for example, installations are simplified in that they are patched in and out of our return air duct, right? They're pulling a volume of stale air out, throwing it outside, replacing it with fresh air. And it just asks us to do a bedroom count, simply, right? So instead of those guys coming and saying, well, I got a 2,000 square foot house, how many CFM do I need? Well, frankly, we don't really care about square footage. When we look at 62.1, which I'm sure Ian will elaborate on, I mean, it does look at square footage, of course, absolutely. And looking at air changes per hour, so to speak. But on the residential side, it's a bedroom count because bedrooms are a good indicator of the number of occupants in the house, right? And it's ultimately those occupants that need the fresh air, right? So we're looking at, just to round the numbers off, we're looking at 32 CFM, 31.8, 32 CFM for the master bedroom, considering two people, right? Ma and pa, and then 16 CFM effectively for every other bedroom. So that quintessential 3-bedroom house only needs 64 CFM of continuous ventilation. Whereas again, historically, as an industry, we've been putting in 120, 150. So there really is opportunity to right size equipment and ensure that, we are not adding any excessive additional load to the equipment. Of course, we do want a higher speed to go to in the instances where we might have family parties or different ethnicities will cook more. So we want to be able to push that unit into a high speed. But continuous ventilation, it's actually a very minimal requirement.
Okay, in a residential environment.
Mm-hmm.
And then, Ian, anything to add on that from your own experiences with putting these units in place?
Well, as far as ASHRAE is concerned, in the 62.2, they do use a different formula. It's a 7.5 CFM per occupant plus 3 CFM per 100 square feet. But even then, when you go through that calculation, you're still perhaps a little undersized there. So, there's still some fine tuning to be done. And as Ryan mentioned, there are other things going on in the home. A lot of air exhausting appliances still exist. You've got, the clothes dryers, and you've got central vacuum cleaners, and you've got wood stoves and that sort of thing still in houses. So, it's still a tricky balance, indeed.
Right. I'm also, we talk about how to right size, but then also I understand there are different installation approaches to these mechanical ventilation systems. They can run on their own or in conjunction with furnace systems. Is that correct, Ryan? Maybe you can share some of the best practices when it comes to the installation process to get the most benefit out of these systems.
Sure. Yeah. So there's 3 dominant installation methods, so to speak. So we've got the simplified, which I kind of hinted at just a moment ago, and that is where unit is simply hung in the mechanical room and ducted in and out of the return air duct. On a residential end, of course, that's a furnace or air handler. On the commercial end, we can also do that same concept with a rooftop unit. Or again, an air handler internal to the building. So that's probably the easiest to do, the least intrusive, so to speak, hung by our central equipment, again, patched in and out of the return air duct. Then we have the exhaust ducted. So exhaust ducted, basically, we are pulling from the areas of high moisture or areas of concern. So on a residential end, laundry, bathrooms, kitchen, very typical. And then in an exhaust ducted, we tie back into that return air. In a commercial space, maybe that's spot exhaust for workstations, where perhaps there's fumes that are being created and things of concern. And then finally, as you hinted at, Doug, we have a fully independent system, which is what we refer to as fully ducted. So as that name suggests, not only dedicated exhaust ports in those areas of high moisture or concern, but supplying back into common areas, right? So on a residential end, hallways, bedrooms, family rooms, non-moist areas, and then commercially, back into sort of common areas, right? And eventually it all sort of reaches equilibrium, right? That air kind of intermingles. So that would be our different installation methods. In terms of best practices, it is pretty crucial that we ensure that these systems are balanced, right? So when we look at, especially as we get into larger CFM ranges, imbalance can create building science issues, right? So if we have too much positive pressure, so we have an excess of supply versus exhaust, what we're going to be doing is driving moisture into the structure, right? Into the drywall, into the insulation. And as that moisture moves its way towards the outside of that wall, it of course is going to get cooler and it may condense inside that wall structure. And now we're looking at mold and mildew, which of course, are not popular things with respect to indoor air quality. Too much negative air pressure, and what's going to happen is the building's going to look to make it up wherever it can, right? So all those little cracks and crevices, we're going to have air infiltration, and that air, of course, is unconditioned, right? So that really exaggerates our heat loss, heat gain, can result in higher energy bills. And, not that we have a lot of natural draft appliances anymore, but in those instances, of course, that could create backdrafting of appliances. But at the very least, what we can see is chattering dampers on bath fans, range hoods, difficult to open doors. And, nowadays with people spending what they're spending on homes, the last thing they want are these little inconveniences, of course, right? So that equalized, balanced system is crucial. So most systems are typically done via either a differential manometer on the residential end, and a lot of units will have ports right in the door. So we're inserting our hoses, reading the differential pressure across the core, looking at the corresponding chart to tell us what the CFM output would be. And code dictates that so long as the two flows are within 10% of each other, it's considered balanced. Some commercial units likely won't have those ports. So we're looking at something, TSI, I'm sure probably has something to that nature, like a pitot tube or a vane anemometer, where we're either, inserting that probe into the ductwork to read pressure, or looking at CFM output at our registers to properly balance that system.
Ian, when it comes to installation, I know you have a system in your existing house. Is that a point of reference for you with respect to what Ryan's been talking about?
Well, that's true. I have an HRV that's a simplified installation, and it's, I had my druthers, I would have had a fully ducted system for sure. The fact that I have to run my furnace fan all the time so that the HRV works properly is a bit of a nuisance. But the main issue I have is that I have a modulating gas furnace that works on a communicating system, and it doesn't talk to my HRV. So there's no way to interlock the two devices without just allowing the furnace fan to run all the time, which is okay because I have a better air filtration system too. So I'm going to run the fan all the time anyway. But I think for the average consumer, I'm not sure that they want to do that. And there's other issues, but I think sometimes HVAC contractors, they make the mistake when they want to sell high efficiency equipment and HRVs and ERVs, they automatically assume that the high-end stuff, the average homeowner just isn't going to buy it because it's too expensive. And in reality, they really should start at the top and work their way down when it comes to pricing. So a fully ducted system with something like a turbo mode and with a zone system, something like that, I think that should be a starting point for a good ventilation system. And then, of course, you can, a builder or a renovator could put in a more simplified system if there was a real cost resistance there. But, I'm thinking on a $500,000 mortgage, a few thousand extra dollars for a high-end HVAC system isn't going to make a difference or too much of a difference over 20 years. So I agree with Ryan. You really want to have a finely tuned system in the building.
Right.
And if I
Well,
may, Doug, I don't know
yeah,
what your thoughts on that are, Ian, but I think as we make that push towards sort of what's already been stated as that end game of net zero, right? And those houses really do become significantly tight. I mean, we're seeing some houses that are under half an air change per hour pre-drywall anymore, right? So, things like you said, the zone register terminals and whatnot. I think we will likely see a push back towards fully ducted systems because it's less penetrations in the envelope, right? Like you said, Ian, HRV, ERV intake and exhaust, clothes dryers, range hoods, bath fans. If we can get rid of things like the bath fans, create a fully ducted system that's effective with emerging technologies like those zone register terminals that you mentioned, that would be great.
yeah.
Absolutely, yes.
I was going to ask the question about, again, kind of best ideas when designing a new build versus a best approach to retrofits. I assume a fully self-ducted or ducted system in a retrofit would be more challenging, and that's where the simplified approach is the way to go in most cases.
I would say, yeah, that's probably the case, Doug. Absolutely. I mean, just a lot a quicker retrofit, certainly, a lot less messy for the contractor and for the homeowner. Certainly, yeah.
Yeah. Well, when it comes to these
Right.
systems, oh, sorry, Ian.
I was just going to say it'd be a new construction or a complete renovation job is where you'd want to really go after the fully ducted system, I would think,
Yeah.
at this point.
So once the system's installed, I'm curious to know about the maintenance and servicing issues for these units, and does this create new opportunities for HVAC contractors in their relationship with homeowners or homeowners or building managers when it comes to maintaining these HRV or ERV systems? Ryan, what's your experience there?
Yeah, I mean, I would say it creates great opportunity. Absolutely. It's a chance to add another line to the invoice, of course, for the contractors that are on the call here, and come back for, depending on the application, that annual or biannual maintenance, right? Looking at cleaning or replacing the pre-filters on the units. Nowadays, a lot of the pre-filters to the core are serviceable items. There's some platforms that offer upgraded filtration, MERV 13s, HEPAs, etc., and those are often disposable or replaceable because of the nature of that high grade filtration. But your standard pre-filters are serviceable. In the event of an HRV, of course, looking at that condensate drain, making sure that it's still clear and allows for proper evacuation. Looking at your exterior hoods, making sure that the intake isn't perhaps clogged up with grass clippings or spider webs, or depending on where you're at, maybe a college kid shoved a beer bottle in there. All these unexpected things. And to kind of just quickly, because I see the one question there, I think from Hans. You're right. ERVs do not require a condensate drain. So, when we're looking at service, that's one less thing. That also adds on the retrofit side a little bit of flexibility in terms of where we may place that. Right. We've seen some instances where an ERV is placed on top of like a linen closet or in a walk-in, right? If space is at a premium, and we are afforded that flexibility with an ERV because of the lack of drain. So.
Right. Ian, I know you had so with regards to manufacturer recommendations when it comes to cleaning, whether it's filters or even the core itself, does that fall under a maintenance?
Well, I know my particular HRV is designed to be homeowner friendly, and the homeowner is encouraged to do the maintenance, but unfortunately, many homeowners just aren't into maintenance, at least in a big way. But in my case, the filters are serviceable. the manufacturer wants the core cleaned once a year, and they want it cleaned in hot soapy water for 3 hours. Now, I know that isn't going to be part of an average contractor's ticket. I mean, that's just too much time. So the homeowner can do that sort of thing. But as Ryan suggests, I mean, it needs a comprehensive look. You've got to inspect those terminals. You've got to, take a look inside, make sure everything's clean. Things homeowners just don't think about. So I agree. They definitely need to be part of it. If you're going to be doing furnace maintenance or heat pump maintenance or whatever, it should be part of a package, I would think, that a contractor would offer to a homeowner. And yes, I mean, they could be on the expensive side, but depending on how many pieces of equipment you have and how much sophistication there is. However, by not taking care of these things, it means trouble down the road that'll be even more expensive. So absolutely, contractors need to be doing this.
Okay.
And one point of clarification there, just so we avoid homeowners or contractors creating undue issues, the popular service method for HRV cores, again, because they're plastic, aluminum, moisture is not really going to create issue with them, is to wash them, so to speak. An ERV core being a polymer reinforced paper, it's coated with a desiccant. Those little packs that you see in some clothing and food that absorb moisture. So if we were to douse that core or submerge that core, you could literally watch that swell before your eyes. So because it's going to try its darndest to try to absorb as much of that moisture as possible. So the small amounts of entrained moisture and airstream is perfectly fine for them in part of normal operation. But when we overwhelm it like that, we would actually end up damaging or potentially destroying the core. So the general practice for an ERV core is to actually just vacuum it in order to pull any dirt that gets past those pre-filters out.
Okay.
Yes, good point, Ryan. In fact, I have an air filtration system that if it sees water at all, it's over. So the contractor would certainly know how to deal with the maintenance for sure.
Ryan, I don't know if you see, there's a question in the chat area from Mike asking, do ERVs over time transfer less moisture?
I would say, that would be a function of, maintenance that we were just talking about.
Yeah.
I mean, yeah, if we're allowing that system to sort of fall into a state of disrepair, any piece of equipment is going to become less effective. But I mean, with proper maintenance, there shouldn't be any issue whatsoever with respect to effective moisture transfer.
Okay. And we have a question here from Pete asking about what about in hydronic applications where there may not be any ducting? I guess, what are the solutions there?
Yeah, I mean, I would suggest, and I'll let Ian sort of, chime in as well, that would be an opportunity for a fully ducted system. And in new construction, that's exactly the case, right? Is they do mandate a fully ducted HRV or ERV. Ian, on your end?
Yeah, absolutely, fully ducted. And, in a hydronic application in a finished building, I mean, you're going to have to perhaps box in some duct work or find some ways to get at least the distribution side dealt with. But yeah, hydronic application in new construction would be easily done with a fully ducted system. In a retrofit, yeah, there'd be definitely some after work involved in that, for sure.
Okay. We have another question here asking to discuss preheat and defrost cycles, especially using ERV in the Canadian climate. Do we not lose any efficiency gain by adding preheat?
Yeah, so when we look at ERVs, for many, many years, decades even, there were some manufacturers that said they weren't suitable in northern climates. But looking at other manufacturers, there's been functioning models in very cold climates, Iqaluit far up north, Alaska even, and they're perfectly functioning. It is just all about having a proper defrost cycle, as that individual sort of hints at. And typically what that is going to be temperature initiated time defrost is what they refer to it as. So there's thermistors on our intake. And as the air is coming in, unit senses, okay, we're getting a little chilly. I'm going to isolate, a lot of units will feature positive shutoff dampers. So they will close, prevent the fresh air from coming in and freezing that unit up. And we'll either have an exhaust-based defrost, whereby we're taking conditioned air from the building, throwing it through the core, exhausting it outside to bring that core temperature back up. Or some of the units, the more expensive units, often will have a recirc defrost. So both intake and exhaust close off, and we're actually recirculating between the building and the unit. Certain instances, of course, we probably want to avoid recirc defrost. If we're having manufacturing processes where there's chemicals or welding fumes in the air, nail salons, spas, stuff like that. But in a residential application, exhaust defrost is typically okay. With respect to preheat, we would actually typically suggest doing post-core heating. And there is a calculation that we look at, where we look at total air volume, the sensible recovery efficiency of the unit. So therefore kind of looking at the inverse, what's left, what we need to make up for, and providing either electric resistance or a hydronic coil post unit to bring that air volume back up to proper temperature. The unit should be able to handle itself and take care of protecting itself with its defrost cycle. It's more about making sure we introduce properly tempered air back to the system, right, in my opinion. Yeah.
Well, here's another question having to do with the dry winter weather. How can one find a proper balance with a drier home in the winter season, and yet the need for fresh air without driving down the humidity even lower? So how do you keep that moisture in the home in the winter months?
Ian, do you want me to take that one?
I'd argue, I would just argue that the ERV is the best way to go in that situation, because it's going to at least preserve some of the moisture, prevent some of it from being dumped outside. So you're going to retain at least a minimal level of humidity. And it really, I guess, depends on the building. The newer buildings, the ones that are more tightly sealed, the ones with triple glazed windows and that sort of thing, they can actually tolerate a higher humidity level. So you can still run 35% RH in the coldest day of the winter, whereas in my house, for example, that would be not a good idea. The windows would be soaking wet. So it really does depend, but on the building structure, how well sealed it is. But certainly in older homes, as you mentioned earlier, Ryan, an HRV is going to dump a lot of moisture outside. Now you need a humidifier. I don't know how many times I've seen improperly sized humidifiers that are typically too small, and the flow through panel types will just keep dumping water down the drain all winter and never reach the humidity level that the homeowner wants. So I would say an ERV would be the best way to solve that particular problem.
Yeah,
Would you agree?
I would entirely. I mean, and in some instances, it may not be entirely the answer. We may need to supplement with mechanical humidification or dehumidification seasonally, because there are some buildings, some homes, that when they get extremely tight, there just is a need for more equipment and better systems. But that ERV, if we were to look at, using a TSI meter, for example, and graphing the curve of the humidity seasonally, we are going to see that roller coaster, if you will, with an HRV, right? In the peak of summer, high humidity, maybe feeling clammy in the house, in the depths of winter, over drying. So that ERV is really going to level out that ride, right? You're not going to get those wild swings. So in a lot of instances should be enough to help us solve issues, but there will be instances still where it's not entirely the answer. We might need to supplement.
Okay.
Right. True enough.
Here's kind of a general one, and hopefully Ian or well, both of you can address this, but what emerging technologies are you seeing in the world of HRV, ERV? So what's leading edge? What's coming? What's new?
What I've been seeing, Ian hinted at it a little bit as well. We have things like some people call them zone register terminals. So looking at that fully ducted installation prior, what the issue was there is, you would put in a larger unit, 150, 200 CFM unit. However, that's, at 0.2 inches of static pressure typically is what they're rated at. So by the time you get your duct work throughout the house, you introduce more static. The realistic suction at one of those bathroom ports, for example, might only be 30 to 50 CFM. And so when you go into high speed, that's still a pretty weak bath fan, right? So when we look at odors lingering, moisture on the mirror, getting out of the shower, there were still some consumer complaints. So these zone register terminals, when the unit goes into high speed, the push button that initiates that call, that register will go wide open. All the others will close. So we will focus that suction right there. Other things with ECM motor technology, even PMSM motors now, permanent magnet synchronous motors in some higher end units. We have the ability to completely custom program our airflows, dial it right into exactly what we need. And there's some manufacturers out there now that are actually offering self-balancing on initial install. So, that process, which unfortunately in some instances, does go unaddressed because, we get it. Guys are throwing units in very quickly in the new construction sector. This eliminates the potential for building science issues because of that lack of balancing.
Okay. Ian, anything to add on that? Anything you've...
Well, what I've been seeing is as Ryan mentioned, these efficient motors and things like that. You'll often see the ERV or HRV will have a Energy Star rating on it as most efficient, and I guess that's where the battleground is right now. And I think there are several manufacturers out there who are bringing in systems. There's one from Europe, Zender. It's a system that uses 2 pipes to every room. It's a very expensive system. But it's nicely configured in the sense that it has MERV 7 and MERV 13 filtration, uses efficient motors and that sort of thing. I'm not sure. One of the issues they're having is they can't get Energy Star rating because they're using electric preheaters for defrost. And of course, I've spoken to one of their reps and they tell me that the passive defrost system ultimately ends up in the same amount of energy loss as their preheaters do, but apparently Enercan doesn't buy their argument. So, and there's another company called Centrotherm that's working on a multi-pipe system as well. So there's that to look at for sure. But I think, as Ryan has said, it's the energy efficiency calculation that's going to be the most attractive going forward, I think.
Okay.
Yeah, the Zender stuff has sort of been, on the bleeding edge with, the passive house types.
Yeah.
A nice alternative to that actually has been, it's the same with Venmar Vanny, like the Venmar X series or the Vanny Gold series. Highly regarded as, with a lot of the engineers that are in that space, the passive house or FIAS. To be a nice alternative to Zender, at a better price point, and of course is code compliant, has the cold weather testing that Zender doesn't, and you mentioned filtration. That platform has an optional HEPA insert as well. With IAQ being top of mind right now.
Very good.
Oh yes, I was looking at their balancing protocol with electronic sensors. It's a really nice unit, actually. I think it's a Van unit that we're talking about. So yeah, there's some good stuff.
The new trying to think, that's the virtual air technology that you're talking about.
Yeah, the Virtuo, yes, that's the unit. Nice product, yeah.
With that, I think our half hour is up. Gentlemen, I'd like to thank you both again for participating today in today's webinar and sharing your industry knowledge. It's very helpful. Also, thank you to TSI for sponsoring this edition of 30 Mechanical Minutes. And of course, thank you to everyone who joined us on the webinar today. A recording of this session will be available on our website, hpacmag.com, in the days ahead. So until next time, farewell and thank you all for taking part today. Ryan, Ian, thanks guys.
Thanks so much, Doug.
Thank
Thanks,
you.
Ian.
Thank you. Goodbye, Ryan.